Alright, hey guys, what's going on? So today we are going to be talking about tetrads. So I've mentioned tetrads before, only in brief, and so in this video we're going to go into them in a little bit more depth, and this is going to be sort of the kickoff into Ashtekar variables and a further deep mathematical deep dive into quantum gravity. So with that being said, make sure to hit that like and subscribe button. Make sure to go into my Patreon page if you want to support the channel, or you can also become a member. Now, without further ado, let's get straight into the topic. So we're going to talk about tetrads today. Tetrad components they can sort of be thought of as the square root of metric tensor, and we're going to see how this works. So with them, we gain the ability to perform Lorentz transformations at every point in space-time. And to formalize our understanding, we're going to begin by recalling the basic definition of a vector and a covector. So vectors, again, vectors are notated in this way, in which the basis vectors are these partial derivatives, okay, because they're linear, they make up a vector space, and so this is what we're going to call a vector in. And we have these vectors live at every point in space-time. We've sort of talked about this before in our GR playlist. And then we have covectors, right? So covectors, again, we have this downstairs index, and the vector space basis is this dx mu, okay? So mathematically, the difference in these is how they transform. So one transforms with the basis, one transforms without the basis. How I like to think of this is co is transformed with the basis. So, and that would be these covectors, which is W, and then contravariant vectors, or vectors, are the ones that transform against the basis, okay? And we've talked about this before in my tensor calculus playlist and a little bit in my GR playlist, so this should be review. So we can model space-time from the perspective of a local traveler by laying down a set of orthonormal basis vectors called a tetrad at each point along the traveler's world line. So suppose we have some geodesic, this black line here, and we can construct tetrads at every point along the geodesic, or every point in spacetime, because geodesics exist in spacetime. So we need, these geodesics sort of permeate spacetime, okay? And the geodesics are the lines within spacetime. You could think of them as lines in which objects travel, okay? And we've talked about how we can derive geodesics from Lagrangian formalism and so forth. And so this is the path of travel in 4D space, right? Time, x, y, and z. And at each point in space-time, we can construct a local inertial frame, or a local Lorentz frame, and that's what I've illustrated here. We have these basis vectors at every point in space-time along the curve. And what I'm specifically doing here is I am showing you that the E0 tetrad, is always going to be is always going to be tangent to the geodesic, okay? And that's going to be important for what we're going to talk about in a few seconds here. The tetrad basis is going to look like this, right? So this E hat, that's what I have here, E hat, okay? And when we have a subscript, right, we're talking about the tetrad basis. If we have co-tetrad basis, is going to be superscripted. Okay, and so we can write these similarly to how we write our covectors and our vectors. And so what we get here is this formalism that looks like this. So at every point in space-time, we can construct a tetrad basis. This is a local inertial frame. And a co-tetrad basis, another local inertial frame, but it's co. It transforms oppositely than the tetrad basis. Okay? Okay, so here's where the big part here comes in. And one of the things when we start talking about quantum gravity, there's going to be a lot of things that are going to be sort of not really independent variables, but there's going to be a lot to keep track of, and I'm going to try my hardest here to help you get an understanding for all of this while continually trying to track all the different types of symbols and stuff that are going to be thrown at us within the next few videos. Okay? And so we can zoom in on one of these tetrad bases. So suppose we're zooming in on this one here, and we see that each tetrad basis is a linear combination of the basis vectors that constitute the space-time. Okay? The time-like basis is tangent to the world line, and I've highlighted this because it's important. This is what's going to make this particularly. Hey guys, what's going on? If you're interested in this video and want to learn more about loop quantum gravity, string theory, and so forth, what you can do is you can become a member of this channel, and you can gain access to all the videos that become uploaded on this topic and future topics as well. Again, thank you so much for your support, and thank you so much for watching. This channel keeps on growing and growing, and I'm very excited to see where this is going to go in the future. So with that being said, make sure to hit that like and subscribe button if you like this kind of content. Make sure to become a member as well. Thank you, and bye.